Okay,
Perfect.
hi everyone. My name is Vadim. I'm a PhD student at University of Turku. My supervisors are Andrei Berdugin and Yuri Potanin. And my talk is about the polarization studies of gamma ray binary LSI plus 61303. And during the talk, I will call it just LSI to be short. And let's start with the description of the source that we are studying. LSI was discovered more than 40 years ago as a gamma ray binary system. The primary component is a giant B star, and 2 talks ago, Pablo Rick gave us an excellent introduction BE binaries. So BE star has a decretion disk around it, which produces the emission lines in its spectrum. Secondary component in LSI is a compact object with unknown nature. It can either be a black hole or a neutron star. The compact object is moving around the primary star on an elliptic orbit and producing variable emission from radio to gamma rays. The main parameters of the system are listed here. The orbital period is about 27 days. And as you might see, the 40 years of previous studies gave
There appears to be some problem with the audio. So Vadim, are you still there? Hello? Can everybody hear me?
Yes.
Yes.
Okay. So perhaps we can, shall we continue with the next talk and then go back to Vadim when he solves the issues with the audio? So Claudia, would you be willing to start your presentation now?
Oh, sorry. Do you hear me?
Okay.
Now?
Yeah, we can hear you now.
Oh,
Yes.
very sorry.
No worries. These things happen all the time. So yeah.
Do you see my slides?
So yeah, please go ahead.
Sorry. It's important to have an independent way to constrain the orbital parameters of such systems, and the optical polarimetry can help us with that. And I just show you light curves of this object. And one thing I want to note here is the phase of maximum of brightness in optics, radio, and gamma rays is about 0.6 orbital phase, and just keep it in mind during the talk. So we observed LSI over 140 nights from 2016 to 2019 with high precision BVR polarimeter dipole 2. And mostly we observe it on 60 centimeter Haleakala robotic telescope T60. Well, we found small but significant variability of the polarization with the amplitude of about 0.2 to 0.3%. And using Lomb-Scargill periodograms, we found that the period of the variability is equals to the 1/2 of the orbital period. So here at the left-hand side, you can find the polarization light curves. There are 2 maxima and 2 minima of them, separated by 0.4 and 0.6 phase intervals. And it's not expected for binaries with a high eccentricity, in which all changes in polarization should occur near the periastron. We have also made a photometry of the system. Here you can see BV and R light curves, and it shows the sinusoidal-like variations, and it's also not expected in case of high eccentricity. So to understand what is going on with the polarization, we developed a simple analytical model. The geometry of this model is shown here at the left side. And in our model, the polarization results from Thomson scattering of the stellar photons on the cloud of free electrons, which moves in an elliptic orbit around the B star. So this cloud can be formed around a neutron star or a black hole due to the interaction with the B star disk material. And the important thing is that the change in polarization in our model is caused by the changing of the scattering angle with the time. And the rate of these changes depends on the orbital parameters. So our variable polarization is also depends on them. And here are some free parameters of our model. And the most interesting for us is an eccentricity, orbital inclination, and the phase of periastron. We fit this model in our data using the Bayesian inference. We fit it simultaneously in B, V, and R bands and in both Stokes parameters. Here are orbital light curves of Stokes parameters. The left column is Q and the right is U, and BVR bands from top to bottom. As one might see, the fit is also shows the sinusoidal-like variations with the distance between the maxima and minima of about 0.5 orbital phases. It's a common feature and it's commonly observed pattern in the binaries with the circular orbits. And on the right-hand side, you can find the posterior distribution for the parameters of the model. And the same posterior are shown here in the table. And the most important thing here is that the best fit eccentricity in our case is about 0.1, and the phase of periastron is about 0.6. And this result is not very consistent with the previously determined values obtained using radial velocity curves, but they well describe the variability of the LSI in radio, optics, and gamma rays. But the question is who is right and who is wrong? And to answer this question, I want to show you one example. On the left-hand side, you can see the radial velocity curves for the classical B binary system, KX Andromeda. And this radial velocity curves based on the different spectral lines. And they look very similar to the radial velocity curves for LSI. And it also shows big amount of intrinsic scatter and so-called secondary bumps. And in the table, you can find that the orbital solutions gave us an eccentricity in wide range from 0.2 to 0.7, and it's very similar to the case of LSI. But as it's a classical binary system, we can observe the secondary component and obtain a radial velocity curve based on its spectral lines. And it was done by Kravtsov in 1998. And here you can see the smooth, sharp curve, which looks like a normal radial velocity curve. And the amazing result is that the eccentricity obtained from this radial velocity curve of secondary component is equal to 0. This result shows that the method which works in case of normal stars can give us a really terrible result when we apply it to the BE binary stars. And in our paper, we argue that the high value of eccentricity obtained from radial velocity curves is spurious and affected by complex kinematics of a gas motion in the BE star disk. And the conclusion is that it's very important to develop the other methods of constraining the orbital parameters in such a complex binary systems like the LSI 61303 and the high precision polarimetry technique, which I described briefly in my talk, is one of the possible methods to do that. So maybe I a little bit over time, and sorry for this Zoom problem. And here is my conclusions. Yeah, we observed LSI over 140 nights. We found orbital variability of its polarization, and we modeled it with the analytical model. We obtained the new sets of orbital parameters, which better describes the multivalent variability of the source. And we show that the polarimetry is an extremely important tool in astronomers' hands. So thank you.